Enterovirus D68, EV-D68, has been increasingly associated with severe respiratory illness and neurological complications in children worldwide. However, no vaccine is currently available to prevent EV-D68 infection. In the present study, we investigated the possibility of developing a virus-like particle, VLP-based EV-D68 vaccine. We found that co-expression of the P1 precursor and 3-CD protease of EV-D68 in Pichia pastoris yeast resulted in the generation of EV-D68 VLPs, which were composed of processed VP0, VP1, and VP3 capsid proteins and were visualized as 30 nm spherical particles. Mice immunized with these VLPs produced serum antibodies capable of specifically neutralizing EV-D68 infections in vitro. The in vivo protective efficacy of the EV-D68 VLP candidate vaccine was assessed in 2 challenge experiments. The first challenge experiment showed that neonatal mice born to the VLP immunized EMs were fully protected from lethal EV-D68 infection, whereas in the second experiment, passive transfer of anti-VLP sera was found to confer complete protection in the recipient mice. Collectively, these results demonstrate the proof of concept for VLP-based broadly effective EV-D68 vaccines. Introduction. Enterovirus D68, EV-D68, is a virus belonging to the enterovirus genus of the Picornaviridae family 1. Like other enteroviruses, the genome of EV-D68 is a positive-sense single-stranded RNA of 7.4 kb and contains a single open reading frame, ORF, that encodes a large polyprotein 1,2. This polyprotein can be processed to produce 3 precursor proteins, P1, P2, and P3. Subsequently, P1 precursor is cleaved by viral protease 3CD to yield 3 capsid subunit proteins, VP0, VP1, and VP3, all of which co-assemble to form viral capsid shells. After viral RNA encapsidation, VP0 may be further cleaved into VP2 and VP4 via an autocatalytic mechanism too. A crystal structure of EV-D68 virus shows that the EV-D68 viral capsid is made of 60 copies of each of VP1, VP2, VP3, and VP4 subunit proteins, and it possesses structural features typical for enteroviruses, such as 3-fold propeller-like protrusions, star-shaped 5-fold plateaus, narrow depressions, canyons, surrounding each plateau, and hydrophobic pockets inside VP1 and directly beneath the canyon floor 3. Recent studies have identified neuron-specific intercellular adhesion molecule 5, ICAM5/telencephalin, and sialic acid as 2 cellular receptors for EV-D684-6. EV-D68 was first identified in the United States of America, USA Indiana 19627, and was once considered to be a rare cause of respiratory disease, with only 26 cases reported between 1970 and 2005 in the USA 8. However, in the past 10 years, the incidence of EV-D68 infections has remarkably increased all over the world 9,10. In particular, a nationwide outbreak of EV-D68 associated with severe respiratory illness occurred in the USA in 2014, resulting in a total of 1,153 confirmed cases including at least 14 deaths, and it is the largest and most widespread one of EV-D68 outbreaks ever recorded in the world. www.cdc.gov web link. Coinciding with this outbreak, 120 acute flaccid myelitis, AFM, cases were reported in the USA, suggesting that this AFM cluster was likely associated with EV-D68 infection 11. Indeed, several cohort studies confirmed that there is an association between EV-D68 and AFM 12 to 14. Thus, EV-D68 infection can cause not only severe respiratory disease but also neurological damage. Over the past 3 years, a significant number of cases of EV-D68 infection have been reported in different countries in America, Asia, or Europe 15 to 17, indicating the continued circulation of EV-D68 around the world. Clearly, EV-D68 has posed a serious threat to children's health, and therefore development of effective EV-D68 vaccines should be prioritized. In addition, based on VP1 gene sequences, EV-D68 is divided into three major clades, designated A, B and C, which are currently circulating worldwide. 10. Virus-like particles, VLPs, which can be produced in recombinant expression systems and resemble inactivated authentic virions in structure and immunogenicity, constitute an effective platform for vaccine development, as showcased by the successful commercialization of VLP-based human papillomavirus and hepatitis B vaccines 18,19. Previously, our group has produced VLPs for a number of enteroviruses associated with hand, foot, and mouth disease, including Enterovirus 71, EV-71, Coxsackie-virus A16, CVA16, and Coxsackie-virus A6, CVA6, and demonstrated their protective efficacies in preclinical studies 20 to 25. In this study, we investigated the possibility of developing a VLP-based EV-D68 vaccine. Our results showed that EV-D68 VLP could be produced in Pichia pastoris, P. pastoris, yeast, and this VLP antigen elicited neutralizing antibodies capable of protecting mice against lethal EV-D68 infections, indicating that EV-D68 VLP is a promising vaccine candidate.